First of all, let me welcome everyone to our virtual exhibition booth at IT 2020. Our next session that we just starting that is going to be overview of 3 research projects funded by Stride Center at University of Florida. That these research projects have developed methodologies, new basically research around the topics in highway capacity manual as well as big picture mobility analysis. Our first presenter is Dr. Nagy Rafael from NC State University, and first presentation is entitled as Assessing and Addressing Deficiencies in the HCM Weaving Segment Analysis. So, Nagy.
All right. Good afternoon, everyone, and thank you for being at the session. Just want to also recognize the co-author and contributor to the study, co-PI Dr. Lily Leftariado from Florida, Behzad Agdashi, former NC State, currently at the University of Florida, Ehsan Amini, and Deshang Chu, graduate students at Florida at NC State University. I do want to acknowledge the financial support of Stride. Obviously, we are one of the 10 universities that are partnering within the Stride UTC. So, quickly, the outline of my short presentation will include an introduction, assessing the limitation of the current HCM method, the data collection, model development, evaluation, and finally, the summary of the work and possible future additions. So in terms of introduction, obviously weaving sections or segments are considered to be very critical. They are very often what causes bottlenecks on freeways. In the past, we've identified weaving segment by configuration. It used to be called type ABC. Now there is a new nomenclature. But in general, we characterize these as either ramp weaves or measure weaves. The weaving analysis has began way back 7 years ago in the very first HCM, 1950, and has been updated ever since, with the current version really developed as part of the HCM 2010. The actual research leading to that latest method was done under NCHRP 375, and that particular research included 11 national sites. Most of them were measure weaves in the data set. So as part of this study, we try to identify and address some of the deficiencies in the weaving method through improved modeling and simplification. So let's start with some of the limitation. One of things that strike you, particularly if you are working this manually, is the complexity of the method. There's, as you see on the right-hand side, there's a flow chart of the methodology, calculations of maximum weaving lengths, estimation of capacity, estimation of lane changing rates for weaving and non-weaving vehicle, speed for weaving and non-weaving vehicle, and then aggregating these into a single speed to determine the level of service. So obviously, like any modeler, anytime you have too many submodels, each submodel will come with its own difficulty and errors, and generally speaking, those individual errors will compound to the overall error of the method estimation. It's also very difficult to calibrate. If you want to see how good the model is working, to actually begin to estimate weaving and non-weaving speed in the field is very difficult. And as I mentioned earlier, the method was calibrated mostly for measure weaves. The capacity model, which is listed here in that equation, make a couple of assumptions. One is that using this term VR, which is basically the ratio of the weaving flow to the total flow, provides equal weight to both the ramp, on-ramp flow, and off-ramp flow. And in general, those we think ought to have different imbalanced effect on the capacity and on the speed. Secondly, which is kind of an interesting phenomenon, is looking at the definition of VR. If you maintain the same weaving flow, but you increase the non-weaving flow, in other words, increasing this term V, as you increase the non-weaving flow, you basically increase capacity, which again is not appropriate, that increasing a flow would increase capacity. Capacity should be really a value that should not be dependent on the total flow rate. And finally, and based on practitioners' input, discontinuity in segment analysis. And what I mean by that, very often when you did an analysis of, let's say, an on-ramp followed by an off-ramp as merge and diverse segment, but then you added an auxiliary lane to convert them into a weaving segment, you could see some difficulty or even some discontinuity in performance. Sometime even performance would get worse under those cases. So that's those kind of limitations begin to tell us that we need to be taking a fresh look at that method. Additionally, and I've given you an example here on the right, sensitivities. The short lengths here that you see, we've changed in that particular example, the short lengths of the weave from 500 to 2,000 feet. We ran the existing method right now. As we would expect, the longer the length, more lane changes occurred. The longer the length, the weaving speed increased. However, the non-weaving speed, which also should be impacted by the length, is fixed. And now, if you think of a weaving segment, most of your volume is going to be non-weaving, freeway to freeway. There'll be some in and out, but 80 to 90% very often you're going to have non-weaving traffic. So if that non-weaving traffic is independent of the length, then essentially the overall speed also becomes much less sensitive to the length of the segment. And as you can see here, by quadrupling the length from 500 to 2,000 feet, the density just dropped by about 6%, which again, basically density has to do with the amount of space that you have. And given that you have the same number of lane, but 4 times the length, one would expect density to be a lot more sensitive to length. And again, the effect of the weaving maneuver being balanced. And therefore, we began to think maybe there is an opportunity to address some of these limitations through this research. So where did we get the data? The data collection, we decided to be also very appropriate is to pick one type of weaving segment, with what we call ramp weave or type A weave in the past. And essentially that's a weaving segment where each of the weaving maneuver will have to make a single lane change to enter or exit the weaving segment. The reason we picked ramp weave was motivated by essentially the 375 project included only one usable ramp weave in its database. So we felt we could contribute to at least in that part. And we used 3 data sources. The one usable segment from that NCHRP study, which was a Maryland site. We collected 6 new sites in North Carolina using drones, as you can see on the right-hand side, the drone that was used, and a screenshot of the drone video, which was taken about 400 feet above each of the sites. And finally, with the University of Florida help, we collected a new database primarily taken from loop detectors on some freeways in Utah, 8 sites in Utah and California. And all the data were essentially extracted and mined both manually or using some video image processing. I can't go into those details in this short presentation. One important aspect with the loop detector data, however, is we made sure that each one of those sites had at least 4 sensors. And the sensor would be the one both on the upstream and on the on-ramp, downstream and off-ramp. So we would know exactly the on-ramp, off-ramp volume, as well as the mainline volume. And some of the site also had a sensor right in the middle of the weave. So that enabled us to provide some decent estimates of the different flow rate, the flow rate from ramp to ramp, from freeway to ramp, using some observation and some estimates of how much those flows were. One thing that is important when we do HCM analysis on a segment level is to limit the data to undersaturated condition. I'm again showing an example here of the speed versus the different sites. And you can see as soon as the speed dropped below 40 miles an hour, we essentially took that data out because we do not want to be analyzing oversaturated segment. Anytime a segment becomes oversaturated, that answer needs to go into the freeway facility analysis to look at queuing, dissipation, and queuing generation. So based on this, we ended up with a very large data set, and we began to think about the model development. And I want to spend a little bit time on this slide because it really is consistent with our motivation, which is both to simplify and enable consistency. So by trying to simplify the analysis, we go directly to the jugular, if you will. We go directly to estimating the average speed on the segment, which is essentially one step before you estimate the density. What does they do? Based on that, our approach enable consistency across all the analysis. And the way we do that is we start by saying we expect the speed on the weaving segment to be always either equal to or lower than the speed on a basic segment that has the same total volume and the same number of lane and the same free flow speed. So our conceptual model is actually very simple. It's the speed in the weaving segment is equal to the speed on a equivalent basic segment minus what we call here a speed impedance term due to weaving, which is SIW. So the interesting thing here is now we're beginning to predict speed on one type of facility as it relates to a basic segment. And you can begin to see that this could be done not just for weaves, but also could be done for on-ramps or any type of freeway segment. So let's talk a little bit about SIW. What do we expect? We expect that the longer the weaving segment will be, we would expect the speed to go up. In other words, we would expect SIW to go down. Makes sense. So that's the down arrow that you see here. Again, if you have more lanes for the same, everything else being the same, you would expect the higher number of lanes, the more ease it is to change lane, and therefore we would also expect that the speed will increase or SIW will decrease. We also want to make sure that once the volume becomes very low, that we would approach the information of a basic segment. The lane changes here would be almost equivalent to a discretionary lane change on a basic segment. And finally, we think, and this is something that was born with the model, that we expect that the ramp to freeway volume would have a much stronger impact than the freeway to ramp volume. So we talk here about model 1 and model 2. And in reality, you could call this model 20 and 25. We experimented with a bunch of models, and then we ended up picking those two as good candidates for the particular approach. And the model are very consistent with what we just talked about. If you look at SIW, which is the rightmost term in this equation, in any one of those two equations, we have coefficient, 5 coefficient in one, 4 in the other. The coefficient have to do with whether ramp to freeway volume has more of an impact on SIW, whether the number of lane, NL, has an impact, whether the length of the segment, LS, has an impact, and of course this V minus 500, this basically takes that equation out altogether when you have very low flow rate within the weaving segment. So in essence, this is the model that we tried to calibrate, and we ended up picking model number 2, and the reason we'll talk that about in a minute. How do we calibrate? We basically took 20% of the data randomly for validation purpose, and then use the other 80% for training or calibration. And our objective was to minimize the root mean square error. The reason here, this is not a linear model, so we look directly at the root mean square error as our objective function. And it's simply is the square root of the average of the square error, which is each one of these observations is a 5-minute observation of observed speed and predicted model speed. And the number of observations were quite large, about over 11,740 for the training data set. So in essence, this is what we attempted to do. The model itself was shown here, Not a lot of variation between model 1 and model 2. And as I said, we did pick model 2 since it generated a slightly lower error. So basically the model error is plus or minus 4 miles per hour, which is actually quite a good fit to the large data set that we have. So this essentially is the speed equation that one could use directly. No new input, anything that is done with the current method. All the data are available here, whether it's the freeway to ramp, ramp to freeway, etc. All of these are available, and no new data is needed to calibrate or to use this particular model. One of the most important contribution is once you have this model, one can calculate capacity directly consistent with the model. So we don't have a capacity model that is inconsistent with the speed model. And it's a very simple way because in the HCM, we determine capacity to occur at a density of 43. And we kept that definition here as well. So on the left-hand side, we substitute for the speed at capacity, which is capacity divided by 43. We calculate the speed at the basic segment for that capacity, which is going to be obviously less than the capacity of a basic segment. And then we also calculate CW on the right-hand side, which is the individual lane volume within at capacity. So again, without a lot of the mathematical computations here, this turned out to be a quadratic equation in CW, and it can be solved closed form solution analytically. So you can come up with a number that is consistent with the speed. And what we did here was just to look at some of the differences. We took an example problem from the HCM chapter 27. And for that particular example, we used our capacity model. And what we did was estimate a capacity here in about 2007 passenger car per hour per lane, giving a volume to capacity ratio, as you see. That compares with a HCM6 capacity that is slightly higher, which leads to a lower V over C. So differences are not huge, but nevertheless are important. Now, we said the 80% on the training. This is the 20% on the validation. And what is plotted here are observed speed on the y-axis and predicted speed on the x-axis. And as you can see very clearly, with tremendous amount of data, the HCM6 tend to underpredict the speed considerably. You could see here the blob on the left is all above the 45-degree line, while the model that we have more or less at least within the 60 to 75 mile per hour is pretty much on both sides of the 45-degree line. In fact, the error in validation was about 9 miles per hour with the HCM, and with about very close to the 4 miles per hour in our recommended model. So we feel also that based on the new data that our model should be predicting slightly higher capacity and slightly higher speeds. Now, the next few slides, I'm just going to show you very quickly some sensitivity analysis. The first one, which one I alerted to earlier, is sensitivity to speed. And you can see here, the blue lines represent the HCM predicted speed for different section lengths under the conditions that are shown inside the graph. And it's pretty much virtually a constant value here, while our model is sensitive both to the length as the speed goes up, as the length goes up, and it, of course, flattens out. But most of the speed gains are happening in the low to medium range of maybe 300 to 1,000 feet. And of course, they also are sensitive to the number of lanes, with the higher number of lanes having the higher speed. Just notice, by the way, that the amount of loading on the network is still the same, 1,400 vehicles per hour per lane. The next one has to do with the capacity model. And as I said here, we are predicting slightly lower capacity than the HCM, but that does not mean it translates into lower speed, because our speed model is a lot more appropriate and tied to the capacity model. But again, what's important here is the range of capacity for HCM compared to our model. We provide a much broader, wider range of capacity based on the length of the segment and on the number of lanes. Next is the sensitivity to ramp to freeway volume, one of the weaving volume. And again, as you can see, we do provide a lot more sensitivity to the flow rate, because the model actually provides higher weight to that particular ramp to freeway volume. HCM provide also sensitivity, mostly linear sensitivity, as opposed to the nonlinear one in the model. And a couple more slides here, the effect of traffic volume. And as you can see here, we basically under 500, we're at the free flow speed, huge sensitivity of speed to the total flow rate compared again to the HCM model. So in general, what we're seeing here is the models that we provide or we propose show sensitivities across the board when it's compared with the HCM model. I'm gonna leave you with this one slide, which is the one we talked about earlier, which is adding non-weaving traffic. So here, we're keeping the weaving flow the same. We're adding non-weaving flow. So essentially, we're increasing the total flow rate. We expect that capacity should not vary by increasing the flow rate. And that's what our model would show compared to what the HCM shows. If the more flow rate you had, the higher the capacity becomes. Again, something we don't think is appropriate. So let me complete this by summarizing what we've done. We've collected new and obtained previously collected data at ramp weaves, 15 sites. Framework is very simple. We start and we end with a speed model from which you can calculate directly the density, not a lot of work to do. It is working for type A weaves. It does have excellent fit to the data with an RMSE of about 4 miles per hour. Didn't talk too much about the literature, but it does confirm a lot of what we heard both in the literature and anecdotally, that the HCM model tend to overestimate density or underestimate speed compared to the field data. On the other hand, even though it does predict slightly higher capacity than our model does, we showed that our models are very sensitive across the board, complete to the model. And then we would recommend in the future that a similar approach would be used both for merged and diverse segments. And those models could be, all we will have to do is just change some of those alpha and beta parameters and then still be consistent across all of these methods. Just to let you know, the final report has been submitted for this study. It is under review right now. We expect to have it released in the fall. So, and that completes my presentation. I do thank you for your attention. If you have any questions, please feel free to contact me by email at the email address shown here.